So couple reminders. The trigonometric substitution is primarily when we see a sum or difference of squares in a problem. This is the last one that we were working on, and we see this difference of squares down there. And it's usually when regular substitution won't work. And regular substitution wouldn't work here because we would let u equal x squared minus 64. When we take the derivative of x squared minus 64, we get 2x. And that derivative is nowhere to be seen inside this integral, so regular substitution won't work because the derivative of u has to be in there somewhere. We use three possibilities for the, well, yeah, I can draw it this way. We use three possibilities for trigonometric substitution: sine, secant, or tangent. Those are the only three we use: sine, secant, or tangent. And the identity for sine and cosine you all have down pretty well. That one looks like this. These triangles help you to remember the identities that you'll need for trigonometric substitution. So you want to get fluent moving through these triangles. Typically, when we use sine, secant, or tangent, I will do it with a little factorization first so that we always have a 1 here. It's a little easier to see which identity to use when you have a 1 present. When there's the a squared there, it's just a little bit more obscured. So I will always do the factorization to make that a 1. And then here we can see, oh, secant squared minus 1. Hypotenuse squared minus 1 is going to give us the other side squared. So it's a little easier to see the identities that you're going to use when you do this algebra step first to force that to be a 1 with factoring. Yeah?
When we have the 1 minus x squared in the
Square root or wherever, yeah.
Why do we use sine instead of cosine? Just wouldn't it be the same?
You could use cosine. You could use cosine. So you could use all 6 trigonometric functions for substitutions. Wherever you could use sine, you could use cosine. Wherever you use tangent, you could use cotangent. Wherever you use secant, you could use cosecant. You could do that. But we usually just stick with those 3 because you can. So if you look in any books, they're always going to use sine, secant, or tangent and not use the other ones, but you actually could. Yeah, you actually could. If you want to be creative, you could try one of the other functions. Because 1 minus sine squared is cosine squared, 1 minus cosine squared is sine squared. So you could use a cosine instead of a sine. So it's definitely possible. And if you did do that, you would end up with answers that may look a little different, but if you used a Pythagorean identity with your answer, you'd get the same. You'd show that they were equivalent. Yeah, so good question. You could do either. So what we did here, remember the algebra step, which might take a little bit of practice, but you should be able to master it. The idea to get a 1 here is that we want to factor this 64 out to the front, and you look at the x squared. There is no 64. But we use our creative math skills and we multiply it by 1. We multiply it by 64 over 64. So then that 64 is now common. That 64 comes out, and it comes out through a square root. So as that 64 comes through the square root, it becomes an 8 because the square root of 64 is 8. And then when we're left, what we're left with here is the 64 in the denominator and that x squared right there. That's what's left, because the 64 that got factored out would be the numerator there, and that 64 comes out to make that 8. So then the x squared over 64 we write as x divided by 8 squared. We want it to be a single quantity that's squared. And that's where we make our decision, whether we use sine, secant, or tangent. And if it's a difference of squares with a trailing 1, we always use secant. If it's a difference of squares with a leading 1, we will use sine. So we're going to use secant here, precisely because secant squared minus 1 is tangent squared. And our bigger goal Our big tactic is that if we could take these two separate terms, which we can't do anything with, we can't split this square root up with the sum or difference here. If we can combine these into one term, then we can implement the square root. And so we can't take the square root of a sum or difference, but if we can turn that sum or difference into a single term, we can take the square root of a single term. So that is our tactic there. And then the square root of tangent squared is tangent, so this will cancel with that. And we're left with just secant. The 8 cancels with the 8. So that's where we're at. Any questions up to that moment? Up to that spot? Anything that you're not sure about or want to ask about? So then we come to the integral of secant. The integral of secant is one that we talked about Tuesday. It's not obvious what the antiderivative is for secant. Not obvious at all. But we are going to see it quite a bit that hopefully it will become second nature. What we talked about on Tuesday was that the 4 trig functions, other than sine and cosine, they all integrate to some sort of log. So sine and cosine integrate to each other with a minus sign adjusted, but the other 4 all turn into logs. And if they turn into logs, that means we probably can write the integral in log form. And remember that log form says that if the denominator's derivative is the numerator, the antiderivative is this. Natural log of the absolute value of the denominator. And we showed why that was earlier in the semester. And what I talked about on Tuesday was that it's pretty easy. Most of us remember the derivative of secant. The derivative of secant is what? Just the derivative of secant. Sectan, just the derivative. So the antiderivative will be natural log of secant plus tangent. But the way I remember it is that the derivative is secant times tangent. But if we use that memory tool and then just take the derivative of secant and separate it with a plus instead of a times, that's the trick. That is the trick. Now this is in logarithmic form. I'll go through it just once more. If we distribute that secant to the numerator, then our new integrand is going to look like this. And that is in log form. It's in log form because the derivative of secant is right there, and the derivative of tangent is right there. So now it's in log form, so we can immediately cut to the chase. We don't even have to write this step. You're going to integrate secant so frequently that I'll be surprised if you don't get in the habit of just writing this down pretty quickly. And then we have our limits of integration that will need to be converted back to, we're going to have to go back to x's. Okay, so that's where we're at. We've got the natural log of this quantity. We need to convert back to x's. And our gateway back to the x's is through this equation right there. All right, that tells us how to change x's into thetas or thetas into x's. And that equation is used to build a triangle that shows us all 6 trigonometric relationships for theta. So this triangle is going to be how we can convert these things back into x's. So we look at our substitution step. Secant is x over 8. If you wanted, you could convert that to cosine. You don't have to. Secant is x over 8. Secant is hypotenuse over adjacent. So hypotenuse over adjacent needs to be x over 8. Right? Secant is hypotenuse over adjacent. That then leaves us with an unknown side over here. We use the Pythagorean theorem to figure out that side. That will be the square root of x squared minus 64. And that quantity that shows up on the missing side is often exactly what you see up in the problem. Sometimes it's a constant multiplier of it, but it should look really close. The one thing we saw on Tuesday, that if you end up with a plus there instead of a minus there, then you definitely did something wrong. It should look identical or super darn close. So what we can do now is convert back to x's. So secant of theta is x divided by 8. Tangent of theta, if we look at our triangle, tangent is opposite over adjacent. So tangent of theta is going to be the square root of x squared minus 64 all divided by 8. And then our limits of integration, we go back to what they were with x's, which was 8 root 2 and 16. So we are there. That's going to be fun to evaluate. All right. Now we just have to plug in the upper limit, plug in the lower limit, take the difference, simplify it, and we have our answer. So first, let's plug in the 16. Plugging in the 16, we are going to have 2 plus this here, whatever that simplifies to. So 256 minus 64, 192. Okay. And then minus natural log, we'll plug in our 8 root 2, so we'll end up with a square root of 2 plus. When we put that in there, we multiply that together, we're going to get 64 times 2, which is 128. 128 minus 64 is 64. Square root of 64 is 8. 8 over 8 is 1, I think. So double check that when you plug that in, you get 1. And square root of 192, is that a perfect square? I doubt it, but there must. Is there a 4 in there? 145.
I think it should
Or is it perfect
be,
square?
because 256 is a square and 64 is a square.
Right. So what is that? Did you simplify it?
No.
All right. I can simplify it before I post the notes. 192. So factor it out, simplify. We could write this as a single log if we wanted. It's not necessary, but you could write this as a single log. When you have a difference of logs, how does that turn into a single log? What's our log property from algebra?
They're going to be divided.
We'll divide it, right? So natural log of A divided by B is natural log of A minus natural log of B. So we could go backwards and turn it into a single fraction if we so desire. So if not necessary on the exam, but if you wanted to, you could turn this into a single log. Don't even need the absolute values on the bottom really, because that's always, I guess we don't need any absolute values because both of those quantities are positive, so we don't even need those absolute values. And then whatever this simplifies to, I'll put that in there, unless you
It's
already
8 root 3, so it'd just be root 3.
just root 3, thank you. So we get that, yeah. Okay, so trigonometric substitution. You are going to need to do a lot of practice on this because it is very tedious. So here we have integral, and we see a denominator that can't be factored. So when we have a quadratic that can't be factored in the denominator, we use completing the square. Now, if that could be factored, there's a technique that we're going to learn later called partial fraction decomposition. And partial fraction decomposition will be used when you have a quadratic and you can, in fact, factor it. But if you can't factor it, go ahead and use completing the square. So it's not factorable, so we're going to complete the square. So we're going to take the coefficient of x, divide it by 2, and square it. If you divide -6 by 2, you get -3, and if you square -3, you get 9. So that means in order for this to be a perfect square trinomial, we need a 9. So we're going to take 9 away from that 34. So now this piece here is a perfect square trinomial. That's a perfect square trinomial. You know you have a perfect square trinomial if the constant is the square of half the coefficient of x. Then it's a perfect square trinomial. Factors into x minus 3 quantity squared. So let's go ahead and do that. So we have x minus 3 quantity squared plus 25. All right. We have a sum of squares in the denominator. That's great. We could convert this, we could do a u substitution and say let's let u equal x minus 3, and then we would just have like a u squared plus 25 type thing, but we don't have to do that. That's not going to give us that much of an advantage. But you could. The first thing I would like to do at this stage is factor out that 25. I would like it to be a sum of squares with a 1. So factoring out that 25. Well, there is no 25 right here, but if we multiply this by 25 over 25, 25 over 25, now we have a common factor of 25 that can be factored to the front. And let's write what's left as a single square. So that will be x minus 3 divided by 5 quantity squared. And we've got that. All right, so if we were going to use trigonometric substitution, would we choose sine, secant, or tangent? Sine, secant, or tangent? We're going to choose tangent. So the sum of squares is always tangent. If it's a plus, we choose tangent like a t. Plus looks like a t. So we're always going to choose tangent. So let's go through this with trigonometric substitution, and we'll notice some interesting things. So we are going to let x minus 3 divided by 5 equal tangent of theta. Now we have to differentiate both sides of that. The derivative of the left side with respect to x is say again?
1 over 5.
1 over 5. Do we agree? Derivative 1 over 5? If you split that fraction, you could write this as 1/5 x minus 3/5. It's a line. Derivative of a line is its slope, coefficient of x. So the derivative of that quantity is 1/5. And so we will have on the left 1/5 times dx, and on the right we will have secant squared d theta. Okay, and we're going to come over here and do our substitution. So we have 1/25 out in front. The dx in the numerator, if you look down here and multiply both sides by 5, dx is going to be 5 secant squared of theta times d theta. We put the d theta on the right. Down below, x minus 3 over 5, that becomes tangent, so our denominator becomes tan squared of theta plus 1. Little bit of simplification. We end up with 1/5 integral What's tan squared plus 1? Secant squared? So those are the same. Tan squared plus 1 is secant squared. Secant squared over secant squared is 1. So this all becomes d theta. Okay. The integral of d theta is theta. So we have that. From our substitution step, that's how we isolate theta. We inverse tangent both sides. So we would end up with 1/5 inverse tangent of x minus 3 over 5 plus c. If you do trigonometric substitution and you end up with this situation where you don't even need that triangle that allows us to convert thetas back to x's, we didn't even need it here. All we had to do is take the inverse tangent in our substitution step. If you end up with that, what that means is that there was an easier way, and we just missed it. Does anyone see the easier way? That easier way is revealing itself right here. At this stage right here. Don't you know this fact already? That the integral of dx over x squared plus 1, what is that antiderivative? Arctan. So that's arctan of x plus c. That's what we have right there. It's actually in arctangent form already right here. We can go immediately from here to arctangent with a little bit of reverse chain rule. Yeah? All right, so if we look at this, that's in arctangent form. It's just that instead of an x, we have x minus 3 over 5. So this antiderivative will be arctangent of x minus 3 over 5 right away. But then we have to divide by the derivative of this quantity here, reverse chain rule. And if you divide 1/25th by 1/5, you end up with 5/25ths, which is a fifth. So you could use that basic fact plus reverse chain rule. But what's nice about this is that we have our three basic inverse trig function integrals. If you forget them and you just go with trig sub, you'll get the answer anyway. So the bottom line is that even if you've forgotten your basic inverse trig integrals, if you just know how to do trig sub, it will come out in the wash anyway. So if you know your inverse trig functions, that's obviously ideal. But if you just don't notice it or you forget it, it's going to come out correct anyway. So that's kind of nice. So for example, if we had something like this, so if we have the integral of dx over, say we have 2x squared, 2x quantity squared, plus, if we just go plus 1, we could use trig sub there, but we can use just immediate antiderivative. Oh, that's inverse tangent of 2x. It's going to be a plus c. What's the reverse chain rule going to do here? What's going to be the coefficient? Coefficient will be, did I hear half? Will be half. Because reverse chain rule says whatever this is, take its derivative and divide by that quantity. So we'll get a 1/2. So you could do it immediately. If that quantity had a non-1 in it, if we had something like, so let's suppose you had this. So you all try this one. So what if you had something like, let's make this x squared plus 36. So go ahead and do that one. That's a different thing, because that A is attached to the angle. So if you have a non-1, then you have the A. So if we factor out the A, so like in the second one, if we factor out the 36 in red, then we're gonna have a 1, and so we don't have, so then A is 1. So I'll always do it where I factor it out. So in this case, A is going to be 6, and we'll see that we end up with that. But if we factor out the 36, then we can use the purple formula in the top right. If it's a 1, it's just going to be arctangent of whatever's in parentheses below the square. Yeah, I'll show you up here how it'll come out. So let me point out something. We have two formulas up here. My strategies is to remember just this one where you have a 1 and not a difference than one, a number different than 1. If you do have a number different than 1, you know, this is the formula in the chart. They try to generalize. And so this is going to give you the 1 over A inverse tangent of x over A plus C. And the whole point I'm trying to make in the last week is that if you make this a 1, you don't have to memorize this stuff. You only need to memorize the basic formula instead of the more complicated formula. Memorizing the more complicated formula takes more brain power. These ones where that's just a 1 are a lot simpler. You don't have to remember the x over A, the 1 over A. It just will come out in the wash if you just remember that one. And now I'm actually showing you an example where you don't even have to remember that one if you know how to do trig sub. But if you're going to remember one of these, this one's just easier to remember. And so watch what happens here. So you could say, hey, this is in that form of the second one, and you could write your answer down right away. But if you do your algebra here, when you factor out the 36, you end up with the case where there's the 1. And right here, there is no 36, so you think in your mind, whether you write it or not, it's up to you. You put the 36 in, that factors out to that. Now you have x squared over 36, which is x divided by 6 quantity squared. And that is now in our basic form. So the basic form says that this is going to be 1 over 36 inverse tangent of whatever's in parentheses here plus c, but then we have to divide by reverse chain rule, divide by 1/6. So when we divide by 1/6, that turns into a multiplication by 6. So we're going to end up with that, which is exactly this. A is 6 in this case, so you'd end up with 1 over A and x over A. So in the long run, it's a lot easier to just remember the basic formulas and how to do reverse chain rule. You have to use reverse chain rule a million times going forward in Calc 2, Calc 3, DiffyQ anyway. So remember reverse chain rule, and the basic identity is going to be a lot easier in the long run. And if you remember that, that's fine too. Both will work. Both will actually work. All right, so let's try another one. You all try this one. So factor out the 2 in the denominator first. Factor out that 2. But you'll notice that after you factor out the 2, that denominator is not factorable. You can pull out that common factor, but it's not a perfect square trinomial. And it's not a factorable trinomial. So use completing the square. Factor out the 2 and then use completing the square. Here, I'm going to fill my water real quick.
That's kind of cool, huh? Yeah. I like it. That's cool.
So when you complete the square there, what is the constant? What constant do we need on the tail there? If we divide the 6 by 2 and square it, we need a 9, exactly. So we're gonna borrow that 9 from the 18. And so we'll have u squared minus 6u plus 9 plus 9. This is now a perfect square trinomial. So that can be factored into u minus 3 squared. Plus 9. So here, it's in the general arctan form, but not the specific arctan form where you have a 1. So my strategy is to factor out the 9. So if we factor out the 9, then we have a plus 1. Now we're going to the specific arctan form. Then we don't have to remember what goes where. We just have the basic form plus reverse chain rule. And when we factor out that 9, there is no 9 there, so we put 1 there, and the factoring of this 9 comes out there and becomes an 18 because of the 2. And we want this quantity to be written as a single square, so u minus 3 divided by 3, quantity squared. Now we have it written in specific arctan form, not general arctan form. So now we can integrate immediately. This will be 1/18 inverse tangent of whatever's in the parentheses plus c, but then we have to divide by 1/3. The derivative of this quantity in parentheses is 1/3, so we divide by 1/3. Multiply by 3 gives us 1/6 arctangent u minus 3 over 3 plus c.
Did the 1/3 came from the slope of the u minus 3 over 3?
Yes,
Okay.
exactly. So we have to, reverse chain rule says you divide by the derivative of this, and the derivative of that is 1/3.
Oh, right.
Exactly. Because u minus 3 over 3 is 1/3 u minus 1. So we divide by that derivative, reverse chain rule. All right, other questions on that one? Judy, question?
I'm just trying to figure out where you factor out the top and right.
This here?
No, on the previous step. No, right here. Yeah.
There?
Yeah. How do you know what's
How we make it 9 and 9?
Yeah.
So in order to have a perfect square trinomial, you need the constant in the trinomial to be half this coefficient squared. So in order to make this a perfect square trinomial, this constant here has to be the square of half that. So we take half of that and get -3, and then we square it and get 9. So we know that we need a constant of 9 to make that a perfect square trinomial. And we look over here at the 18 and we say, oh, well, let's pull 9 from that 18 and use that as the constant in this trinomial here. So we're just taking the 9 and writing it as 9 plus 9 and using that 9 to make that factor. Right? So this part's going to be a perfect square trinomial as long as that constant is the square of half that. And so we're, sort of like up here, same idea. This part right here, if we want to factor that part, it needs a constant that's equal to the square of half of that. And so once again, up here we needed a 9. And so to get that 9, we're going to say, hey, let's just pull 9 from the 34. And if we pull 9 from the 34, we're left with 25. So this part right here is a perfect square now. So a perfect square always has that property that the constant is the square of half the coefficient of x or u, whatever the middle term is. Other questions on it? Let's take a look at the sign. Since we talked about the general versus specific inverse tangent, let's look at the inverse sine one just for a moment. So the inverse sine one says that if we have this, that is going to integrate to that. So that's the specific inverse sine one. The general inverse sine one says that if you have not a 1, if you have something over there that we call a squared, then this is going to integrate to inverse sine of x divided by a plus c. So that's the general one. The general one has the a in it. And you notice that the general of the inverse tangent has a 1 over a in front. The general for the inverse sine doesn't have a 1 over a in front. So it's harder to remember the general ones because there's this extra a that's sometimes there, sometimes not there. That's why I recommend always having the 1, then it just integrates to inverse sine or inverse tangent or inverse secant. You don't have to think about it. So if we have something like this, if we have, say, the integral of dx over the square root of 4 minus x squared, yes, you could use the general one, but it's much better mathematical practice to understand how to do this and use reverse chain rule. Way better for your skills than just memorizing this general one. Because 9 times out of 10, when you walk out the door, remembering the general formulas, you're not going to remember it 6 months from now. The specific ones are much easier to sort of hold on to. So if we have that, we factor out the 4, it comes to the square root as a 2. This has no 4 in it, so we imagine multiplying by 1. And then we rewrite the x squared over 4 as a single square. Reverse chain rule, super important because we use it all the time. So this also helps practice your reverse chain rule. So it's inverse, it's 1/2 in front, inverse sine of this. What's the derivative of that?
1/2.
1/2, so we have to divide by 1/2. So those halves cancel and we get inverse sine of x divided by 2 plus c, which is the same thing you would get if you used the general formula. But the interesting thing is that even if you forget that this is inverse sine, all you need to know is that when you see a difference of squares with a leading one, you can use trigonometric substitution right here. And if you said, oh, if you just forget or don't notice that it's inverse sine and you could just go right to the answer, if you do your trigonometric substitution, x over 2 equals sine of theta, it's going to come out so fast. So if you do your derivative stuff here, you'll get that. And when you plug it in, you're going to end up with just theta. So we will end up with 1/2 dx. Numerator is 2 cosine theta d theta. Denominator, 1 minus sine squared, which is cosine squared. Square root of cosine squared is cosine. Those cancel. You end up with 2's canceling. You end up with d theta. The integral of d theta is theta. And how do you get theta? You solve this original substitution step for theta, so we get inverse sine of x over 2. So if you get the trig sub down, you don't even have to remember the basic 3 formulas. Although I highly recommend that you do, because it's quicker to know the basic formula than doing trig sub every single time. But if there's no time pressure, you can always do trig sub. And you'll get to the answer anyway. Any questions on any of those ideas? Okay, so let's go to our next integration technique, PFD, partial fraction decomposition, PFD. And PFD is a remarkable technique because it allows us to turn something that's very complicated looking into something that's quite simple to integrate. When you look at this rational function over here, that is not an easy integral. You can't use substitution. You know, you could maybe use trig substitution. This is a quadratic that's not factorable, or it's not, I mean, this is factorable, but it's not a perfect square trinomial. It factors into 2 distinct binomials, which we'll do that in a second. But you could use the completing the square method that we just did and use trigonometric substitution. That's a possibility here. But if you have a denominator that's factorable, which that denominator is factorable, to x minus 2 and x plus 4, in algebra, you were over here, and you were taught how to get a common denominator and go from there to there. That's what you did in algebra, right? Get a common denominator, and you can turn this sum into this single rational expression. Well, when you come back to this form, you think, oh, that's easy, right? Those are both logs. That's a really easy integral, right? This just becomes natural log, because they're both in log form. So it just becomes this. You're like, oh yeah, we like that, right? Those are both in log form. Those are easy to integrate. This is hard. It's like, ugh. Maybe trig sub will work, but maybe not. So when that denominator is factorable, we're going to learn a technique called PFD, partial fraction decomposition. And it's basically what we need to do is figure out how to get back to these partial fractions, the little fractions that combine to build the big fraction. If we can decompose the big fraction into little fractions, the little fractions are easier to integrate. So in algebra, you go this way. In calculus, we go that way. So let's see if we can figure out how to reconstruct these little fractions, to find these building block fractions to build that big fraction. First, we're going to look at the simplest case. And the simplest case is when all of the factors in the denominator are linear. So each of those are linear. So that's what this is representing up here. We've got linear factors. And so if all these factors are linear, this is how we do it. So if the denominator factors into these non-repeating linear factors, the PFD is going to be a constant over each one of those linear factors added together. That's what that says. So, what we're going to do then, this one's already factored for us. So we're going to take our factored form, we're going to take this factored form, and what this whole messy paragraph says is that this must be equal to a constant over x minus 2 plus a constant over x minus 6, x plus 6. That's what that says. If you have linear, distinct factors, so they're not the same, it's not a repeated factor, you put a constant over each of those factors. That's it. And now we have to solve for a and b using algebra. So that is the partial fraction decomposition of that fraction. It's going to turn into a constant over x minus 2 plus a constant over x plus 6. So now we go back to algebra. How do we solve that? Well, we multiply by the denominator to clear out the fractions. So when we multiply by that denominator, both sides, we end up with that. So we multiply both sides by this denominator, x minus 2, x plus 6. When you multiply the left by that denominator, you get just the numerator. When you multiply the right by that denominator, you have some cancellation. So we're multiplying the entire equation by x minus 2 times x plus 6. The x minus 2 cancels when you distribute it to the a term. The x plus 6 cancels when you distribute it to the b term. All right. So on the right, if we distribute, we're going to have ax plus 6a plus bx minus 2b. And if we do a little strategic grouping, we could write this as a plus b times x plus 6a minus 2b. Now we need to figure out a and b. Let me ask you a related question. If you had this going on, if you had that going on, could you tell me what a is equal to?
Yes.
Could you tell me what b is equal to? Right? Obvious. Coefficient of x has to match on both sides. If you have this linear function equal to this linear function, the coefficients of x better be equal. Right? The only way those could be equal is if a is 2 and b is negative 1. Right? Obvious? That's got to be the case. That's all we're going to use over here. When we look to the left, this is 0x plus 8. So on the left, you have a polynomial that's linear. On the right, you have a polynomial that's linear. The only way two polynomials can be equal is if the corresponding coefficients are equal. It's the only way. The only way that this equation can be true is if this coefficient of x equals that coefficient of x, and this coefficient, or this constant, is equal to that constant. It's the only way that two polynomials can be equal, is if the matching coefficients are the same. No choice. So, that gives us a system of equations that we can solve. So this tells us that we have this system. We have that a plus b is equal to 0, and we have that 6a minus 2b is equal to 8. So coefficient of x, match, coefficient, or constant term, match. In the bottom equation, we can divide out the 2 first. So let's just do that before we do anything. Divide out the 2. So we have 3a minus b equals 4. Dividing out 2. In algebra, you learned 2 techniques. One was called substitution. One was called elimination. And we can use whichever technique is your favorite technique. Doesn't matter. You can use substitution or elimination. Does not matter. So if you use substitution, you solve for one of the letters in one of the equations and then plug it into the other equation and then back substitute to get the original. Right. So if you do substitution, you can do it that way. This setup lends itself to elimination. We could eliminate the b's just by adding. Right. If we add those 2 equations, the b's disappear. So if we add those 2 equations, we would get 4a plus 0 equals 4. So a is equal to 1. You could use substitution also, but in this case, elimination is just a little faster. So how do we get b if we know a is 1?
It's -1.
So we plug it into either equation. If you plug in that 1 right there, subtract it, b is going to be -1. If you plug the a equals 1 down here, you have 3. You subtract 3 to that side, you get 1. Divide by -1, b is -1. So once you get one of the letters, you can plug it into either of the original equations and you get the other letter. So now we know what our original fraction, we know how to decompose it. So we are going to have the integral of a over x minus 2. So 1 over x minus 2. And then b, -1 over x plus 6. So our original integral, whatever you want to call it w, call it omega, whatever, this original integral is now that. That's easy to integrate. That's log form twice. So we can now integrate instantly. And there's our antiderivative. You don't have to, but if you wanted to, you could turn this into 1 with log property. So that there's our final answer on it. So that is PFD in its simplest case, when all of the factors of the denominator are distinct and linear. Right?
I'm confused on the a over x minus 2 plus b over x plus 6.
Mm-hmm.
And then in our w equation, it's 1 over x minus 2 minus 1 x plus 6.
Right here?
It's
Yeah.
-1.
That's because of this b. Right here, the b is -1. So when we plug in -1 right here, come on, you can do it. So when that gets replaced with -1, it introduces that negative sign in front, since b is -1. Other questions? All right, let's take our 10-minute break. Or if you're itching to do one on your own, you can start that one. You can't resist, you can't hold back. You gotta go. You gotta go straight into an example. So the technique that we're learning right now is applicable only to linear factors. So our denominator is factoring into linear factors. And if you remember back from algebra, there was a really famous theorem called the fundamental theorem of algebra, which I'm sure you all can repeat. The essence of the fundamental theorem of algebra, and when you get into calculus, in Calc 1 you had the fundamental theorem of calculus. In algebra, the fundamental theorem says that any polynomial that's got some conditions on the coefficients, they have to be rational, the coefficients, you can always factor it down into linears and irreducible quadratics. So if you have a polynomial of degree 8, you could factor it down possibly into 8 linear factors, or maybe linear factors that have some repeated, like a power on them other than 1, or an irreducible quadratic. Everyone clear on what an irreducible quadratic is? It's a quadratic that's not factorable. Right? So it's irreducible. You can't turn it into 2 linears unless you use imaginary numbers. So the classic irreducible quadratics are things like x squared plus 1. You can't factor that into linears unless you use imaginary numbers. You could factor that into x plus I times x minus I, but we don't want to do that in here. So any quadratic that like a sum of squares is irreducible. You could factor it with imaginaries, but that's not what we're doing. So the fundamental theorem of algebra says any polynomial with rational coefficients can be factored into linears and irreducible quadratics. So when we look at this denominator and we go to factor it, this denominator, the first thing we see is that you can factor out an x. So we have a linear, the x to the 1, that's a linear factor. And then we have a quadratic factor, but that quadratic factor is not irreducible. That factor can be factored more. A difference of squares can always be factored. So that is going to factor into x times x minus 1 times x plus 1. So now it's totally factored. So we need to totally factor the denominator before we can do our PFD. So we've got to make sure that we get everything down to linears. And if we can't get it all to linears, any quadratic has to be irreducible. Has to be, something like that, an x squared plus 1 or some different, something that's not a difference. Differences are usually factorable. Okay, so now we want to build our form, the structure of our PFD. We're going to take this integrand and we are going to figure out what the form of the decomposition is. And the theorem says that when you have all these linears in the denominator, the way you build your form is pretty straightforward. You just put a constant over each one of those. So this is the form of the decomposition. Now we just have to solve for A, B, and C. So we are going to multiply both sides by the denominator on the left. If you multiply both sides by that denominator, the left side becomes the numerator, since you just multiplied out the denominator. So we get the numerator. And on the right-hand side, that quantity has to be distributed to each of these fractions. When that quantity, that triple product over there, when that triple product comes over and is multiplied by the first fraction, the x cancels, but you still have the other two factors. So this is going to be a multiplied by x minus 1 times x plus 1. And then when this triple product lands on the middle term here, the x minus 1 is going to cancel. So you'll be left with b and an x and an x plus 1. When the triple product is distributed to this third term, the x plus 1s cancel, And we're going to have c and x minus 1. So there is our PFD equation once we've multiplied by that denominator and canceled the common factors on the right. Now this right-hand side needs to be multiplied out so that we can use the method that we're using right now is called the traditional method. The traditional method is where you turn both sides into polynomials and then you match the corresponding coefficients. So this right-hand side, it's not totally obvious right now what the coefficient of x is or the coefficient of x squared. So we have to multiply this out. So when we multiply this out, we're going to end up with this. We're not quite there yet, but we're getting there. So we have that. Let's see if we can do this in one step here. So I'm going to look at the x squareds first. So there, and there. If we distribute the a and the b and the c, do you see what the coefficient of x squared is going to be? Coefficient of x squared is going to be what?
A plus B plus C.
A plus b plus c. A plus b plus c. All right. Now let's look at the linears. So there are the quadratic coefficients all grouped together. Ax squared, bx squared, cx squared. Now let's look at the linears. No linear from here. The next term here is going to be a constant. Here's a linear, and here's a linear. So the coefficients of the linears will be bx and minus cx. So b minus c will be the coefficient for x. So we're taking the bx and the negative cx. So that'll be the coefficient of x. And now let's go with just the constant. That's only this one, right? This has a linear and a quadratic. This has a linear and a quadratic, no constants. This one has a constant, and that's just negative a. So that goes here. On the left-hand side, we have 0x squared plus 4x minus 2. So let's go ahead and set up our system. So our system says coefficients of x squared have to be the same. So that tells us that a plus b plus c must be 0. It tells us that b minus c must equal 4. And it tells us that negative a must equal negative 2. So that is our corresponding system of equations that will allow us to solve for a, b, and c. What was that?
Gives us a.
Yeah, it gives us A.
So a is 2?
Mhm.
Excellent. So a is 2. Totally agree. Now what?
B plus C equals.
-2.
And
So-
minus equals 4.
So we have a couple choices. We could take that 2 and plug it in up here, and then we're going to have two equations with b and c, right? And then those two equations can be combined with substitution or elimination. So if we can even do this. If we add these two equations, that's not a nice bracket. If we add these, let's see what we get. So I'm just going to add the top two equations. We're going to get a plus 2b equals 4. And so c disappeared if we add those two. And then we can plug the 2 in there for a. And that's going to give us 2. If we subtract that to the right-hand side, we're going to get 2b equals 2. So b is 1. Everyone tracking on that? So if we add the top two equations, we get a plus 0, which is a, b plus b, which is 2b, c plus negative c is 0. 0 plus 4 is 4. Plug in the 2 for a, subtract it to the right, divide by 2. And if b is 1, we can plug it in right here to get c.
-3.
C is going to be negative 3. So that tells us c is -3. Plugging in b equals 1 there, you're going to get -c equals 3, divide by -1, c is going to be -3. So now we have all three. A, B, C. So our integral, whatever we want to call it, I'll call it W. Our original integral is now equal to the integral of 2 divided by x. So we're using our form right here, 2 over x. And then b over x minus 1. So b over x minus 1. And then c minus 3 over x plus 1. And that minus 3, we can pull the minus in between as the operation. So once we get a, b, and c, we're just going to plug them right into there. And that's a dream integral. Those are all log forms. Derivative of x is 1. So this is 2 times 1. That one, derivative is that. This one, derivative is that with a minus sign. So this will be 2 ln absolute x plus natural log absolute x minus 1 minus 3 natural log x plus 1 plus c. So once we have all those smaller fractions, they integrate instantaneously because they're all in log form. Yeah? Yep. So we like that. Now, the hardest piece of this is actually probably this algebra in here and getting everything grouped properly. That's probably the hardest part. And let's look at the next. Oh, did I? Oh, I want to do one other thing before we go on to these. I thought I put it in there. Maybe I forgot to. All right, so I want to go back to here for a second. And so we just did something called the traditional method. The traditional method, the standard method, is where we equate those coefficients. I want to show you this alternate method, which can speed things up if you have linear factors. When you have linear factors, this convenient value method is super cool. It goes really fast. So I want to go to this step right here. So this step right here, this is where we decide whether we use traditional versus convenient value. So we have to decide at this point. Do we go traditional method? Traditional method is where we multiply everything out so that we have a polynomial on each side, and then we equate the coefficients. So check out this convenient value method. So let's take this and copy it. And let's come down here. I don't know if this is going to work. Are you going to work? I have to go over here and right click. Should be a way to right click up there. But... All right, so here we are going to use the convenient value method. So once you have divided, or once you've gotten rid of this division up here, once you've multiplied to get rid of this division, this equation now has a domain of all real numbers. This equation has no division by 0. This equation has division by 0, so the domain excludes 0, 1, and -1. But as soon as we multiply by that denominator, this equation, the domain is all real numbers, okay? And the convenient value method says this. It says take your PFD equation and plug in the zeros from the linear factors. So we had 3 linear factors. One was x, and its 0 is 0. One was x minus 1, its 0 is positive 1. And then one was x minus 1, x plus 1, so its 0 is negative 1. So the convenient values, we look at the denominator and we pick the zeros. So the convenient values are x equals 0, x equals 1, and x equals negative 1. All right, so bear with me here. So we've got this equation. We don't feel like multiplying it all out because that's kind of a pain. We can do this. Take the 0, plug it in for every x. All right, on the left-hand side, when you plug in 0 for x, you get that. On the right-hand side, plug in 0. There and there, you end up with negative 1 times 1, so you get negative a. What do you get when you plug in 0 for this term? 0. What do you get when you plug in 0 for this term? Also 0, right? Done. A is equal to 2. Same thing with this. Let's plug this in for every x that we see. 4 minus 2, 2. Plug in x equals 1 here, what do we get? 0. Right? 1 minus 1 is 0, so this term is 0. Now we plug in 1 here. So 1 goes there, we get a 2 there, 2 times 1 times b, so we get 2b. And we get 0. Right, if you plug in 1 there, 1 minus 1 is 0, so that term is 0. Done. Now we have b. Now we plug in negative 1 across the board. Negative 1 there gives us negative 6. Negative 1 here gives, right, 0. Negative 1 here gives 0. Negative 1 here, let's see, negative 1 and negative 2, and they get multiplied together. So that's positive 2 times c, so that's 2c, so c is negative 3. So 2, 1, negative 3, 2, 1, negative 3. So the convenient value method works beautifully if everything is linear. Okay? So that is the recommended choice when everything is linear. But we need that traditional method because when we have nonlinear factors, there's really no shortcut. So we need to understand that traditional method where we equate the corresponding coefficients. We have to use that. All right. The next step for PFD is if you possibly have repeated linear factors. Repeated linear factors. So, for example, right here, this is a repeated linear factor because it has a power of 2, so it's repeated twice. This one down here has a repeated linear factor 3 times. So x minus 2 is raised to the 3rd power, so it's a repeat of 3. It's repeated 3 times. What this says is that for any factor that's linear and it's repeated, it's got a multiplicity other than 1, you need a partial fraction for every power of the denominator. That's what this says. You have a partial fraction for just the linear factor all by itself. Then you have a partial fraction for that denominator raised to the 2nd power, etc. So this one is going to have 2 fractions. This one is going to have 3 fractions just for that one factor. So the PFD here, if you look at our, and they already factored this for us, so we don't have to do any factoring. So it's factored into 3 linear factors, one of which is repeated, so that has a multiplicity of 2. So this is going to be the linear factor with the x minus 6 is right there. But then for the factor here that's got a repeat, we have to have a partial fraction for each power. So this is going to be our decomposition. So for that x plus 2 squared, we have 2 fractions. 1 for each of the powers. X plus 2 to the 1, and then x plus 2 to the 2. Constant in the numerator. Now we multiply the whole equation by the denominator on the left. So that denominator on the left, we multiply, across the whole equation gets multiplied by that. So we're going to multiply by x minus 6. Multiply by that. On the left, you just end up with your numerator. Okay, on the right, that triple product there gets multiplied across each fraction. So this triple product has to go to here, has to go to here, has to go to here. When that triple product multiplies to this fraction, x minus 6 cancels. And there's an x minus 6 in the denominator. Cancels with this x minus 6, which is in the numerator. So that triple product will simplify to a times x plus 2 squared. When we distribute it to the middle term, we get b times x minus 6 times x plus 2. When we multiply it to the third term, the x plus 2's, they all cancel. We get c times x minus 6. So there is our PFD equation. And here's where, yeah, Lauren?
Why do we take x plus 2 and then we also take x plus 2 squared? Because wouldn't that give us 3?
We will get a common denominator. In the long run, if you were given this back in algebra, you would get a common denominator of x plus 2 squared and add them together. You would multiply this one by x plus 2 over x plus 2 and add them together. So what happens is that in order to get the entire numerator, that numerator is squared, right? But there's no x squareds here until you get that common denominator by multiplying x plus 2 over x plus 2. And this one you would have to multiply by x plus 2 squared over x plus 2 squared. You'd also have to multiply them each by x minus 6. So we need to have a fraction for each power in order to get back to what we need here. So it's always going to be that way, that if you have a power of 3, you're going to end up needing 3 fractions in order to reconstruct the numerator. So no matter what this power is, this is going to dictate how many fractions you need. So this being a 2 means you're going to have 2 fractions. This being a 3 means we're going to have 3. So it's just how it works. If you were to start with if you were to start with just that, you would not be able to build back to that. If you were to just start with this and this, you would not be able to build back to that. So you need to have each of those separate pieces raised to each power up to that one in order to build back to that numerator. So you could take this one away and try, take this one away and try, and you won't be able to get back to that. So the process just includes a fraction for each power. And the reason is that because that's what works. If you don't do that, you can't get back to it.
So then how do we know to take the x plus 2 and not the x minus 6?
So we're using, when we build these denominators,
Yeah.
so this denominator gets built from each of them. This is only to the 1 power here. So we only have 1 fraction. This 2 is only on the x plus 2, so that factor, the x plus 2 squared, that factor gets separated into 2 separate factors. We have to end up having a fraction for every power of that.
But then why is the second one squared? I guess this one.
This one here?
Yeah.
Because that's what the rule says. The rule says that we need to have a denominator with each power all the way up to the denominator of what was given. So if this is given to be a power of 2, we're going to end up having to have an x plus 2 raised to each power up to the 2. Let's finish this one and we'll start the next one and we'll see. Jordan?
Yeah, so I guess my question would be, is if we were just rewriting this, the denominator, we would go x plus 6 and then x plus 2 and then x plus 2 as their own individual ones. And if we were following the rules before, we would just separate those out into a over x plus minus 6, b over x plus 2, c over x plus 2. So
The problem is, so if you do
yeah.
what you just said,
Mhm.
if this is not squared,
Yeah,
then you're only going to have b plus c over x plus 2, right? If you had both,
Okay.
and that's just really going to be d over x plus 2. So you'd really end up just with this again.
okay.
Do you know what I mean? So if you don't increase this denominator to a square, if you just made this c over x plus 2, you're going to be back to just that. And that, if you add them together, is not going to be enough to create. So like, think about this. This has a power of 2 in the numerator, right? Ugh, get up there. Power of 2. If you just do this, you cannot get a power of 2,
Sure.
right? Do you agree? If you were to add just these first two fractions, you would have x minus, you'd multiply this one by x plus 2 over x plus 2, multiply this one by x minus 6 over x minus 6. When you add those together, the numerator is going to be linear. The only way we can get that numerator to get up to a power of 2 is to have something down here with a power of 2, so that when we multiply and get the common denominator, this one is you're multiplying by x minus 6 over x minus 6, x minus 6 times x plus 2 over each other, and that one multiplied by x plus 2 squared over x plus 2 squared. The only way we can build up to that square is if we have a square here. So we do it because it works. That's really the bottom line. We do it because it works. And if you try it any other way, you're not going to be able to build up to that square in the numerator. So let's do this one and we'll set up the next one and see how it goes. Okay, so we've got our PFD equation. Here is where, in the last problem, we said we could go traditional method or we could go convenient value method. There is a hybrid method. You can use kind of a little bit of each. So whenever we have some linear factors in here, that convenient value method will be a shortcut, and it will shortcut it a little bit. If we go traditional method here and multiply all this stuff out, it's kind of a long process. If we could shorten it a little bit, that's helpful. So let's do that. Let's shorten it a little bit. If we do convenient value method, what would be an obvious convenient value? Did I hear 6? 6, and that should be an x right there. So if we do x equals 6, plug in 6 on the left, you get 36 times 16, which off the top of my head I don't know, so I'll just write it here. On the right, when we plug in 6, gone and gone, right? 0 and 0. So we plug in the 6 right here, and we're going to get a multiplied, let's see, 6 plus 2 is 8, so we're going to get 64a. Everyone agree with that? Then we can divide out this 16, goes in once, 16 goes in there 4 times. So what is a going to equal? Divide by 4, and a is 9? Do I hear a yes? A is 9? Now that we have a is 9, we have a couple of choices. We could plug it back in up here and rewrite our equation, or we can keep going with another obvious convenient value. And what is the next obvious convenient value?
X equals -2.
-2. Plug it in on the left, 4 times 16, 64. Plug it in on the right, -2 here, gone. -2 here, 0, gone. So we only plug it in here, -2, -6, -8. So -8c. So what is c equal to? -8. So now we don't have a third convenient value. But we can pick any number we want. Right? These convenient values are convenient because they make a bunch of zeros over here. But we actually could plug in any number we want. We're just picking those because they're super convenient because they make zeros. But we could plug in other numbers. I'm going to choose x equals 0 because it makes the left side 0. And it's going to give me another equation. Let's see what it gives us. You can plug in any number you want because this equation has domain all reals. So if we plug in 0, on the left we get 0. On the right we get 4a. Plug in 0 here, we get negative 12b. Plug in 0 there, we get negative 6c. We already have our a and c solved for. So the only one we need is b. Do you see how we get b? We're going to plug in a right there, we're going to plug in c right there, and then solve for b. So that is going to give us the following. We're going to have 0 on the left. 4a is 36. And then we have minus 12b. We don't know what b is yet. And then we have negative 6c. Well, c is negative 8, so negative 6 times negative 8 is 48. So we have that. So this tells us that b is equal to, well, let's just do it. 12b is equal to 70. What's that, 84?
84. B is equal to 7.
So b is equal to 7. So now we have all of them. So we used a kind of a combination there where we had convenient values, but then we picked another value that wasn't convenient, but it was convenient-ish. If we plug in 0, the left side 0, that's kind of convenient. And you can plug in 1. You can plug in whatever number you want. 2. So you might look on this side and say, hey, plugging in 7's kind of convenient because 7 minus 6 is 1. You could do that. So you can pick that number to be whatever you want, and you just sort of pick whatever seems to make the most sense for you. So let's then take this and set up our new integral. So we're going to call our original integral whatever we want. W is a fine letter. So we are going to end up with a is 9. So we have 9 over x minus 6. Plus b is 7. So 7 over x plus 2. And then c is negative 8. So we'll put the negative in front here. Did I say negative 8? Yeah, negative 8. And then dx. So there is our new integral.
Why did you write 8 over x plus 2 to the 6th?
Instead of writing it over what it's supposed to be? Is that your question?
Yeah.
That's a great question. I'm going to blame it on this person.
Raichu.
Raichu. Evil. All right. Cute but evil. So then this is going to be 9 natural log of x minus 6 plus 7 natural log of absolute x plus 2. How do we do that final integral? So this one we're going to think of as 8 to the x minus, 8 times x plus 2 to the negative 2. And so then we add 1 and divide by the new exponent. So for that one, we're going to have negative 8 right there. We add 1 to this exponent and get negative 1. Everyone with me? And then divide by negative 1. So that is going to be 8 over x plus 2 divide by negative 1 or multiply by negative 1 plus c. So we add 1 to the exponent and get negative 1. When we divide by negative 1, it makes it positive. And x plus 2 to the negative 1 is 1 over x plus 2. So there is our crazy answer. Any part of that that you want to ask about? I think the next one will maybe reveal a little bit more about what we were talking about with why you need those extra fractions. So the next one, we have a power of 3. So let's think about this one in terms of what we were sort of wrestling with a minute ago. So when we take our integrand, we see the x minus 2 there. It's to the 3rd power. We need to have fractions that add together that are going to create a square in that numerator. Right? If we just have an x minus 2 in the denominator, we can't build up to that square in the numerator. So we do another partial fraction raised to the 2. So now, if we were to combine these with back in algebra, we would multiply this one by x minus 2 over x minus 2 and add them. That's still not up to a square. That would build up at most a linear. If we multiply this by x minus 2 over x minus 2, we have a single x in the numerator, so it's linear. So we're not there yet. We add a 3rd one. This, that's the 3rd power. So if we're thinking about going from the right side to the left side, now this one we would be multiplying a quadratic over a quadratic. This one we would multiply by a linear over linear. This one we are already at 3, so we don't have to multiply it by anything. But this term here would have to be multiplied by a quadratic over a quadratic in order to add these 3 denominators together. To add these 3 fractions, we would have to have this common denominator of x minus 2 cubed. To get an x minus 2 cubed, we'd multiply this one by x minus 2 squared over x minus 2 squared. And that's how we build up that square in the numerator to match that. So we have to have a partial fraction for every power of the factor. So partial fraction for the 1st power, the 2nd power, and the 3rd power, because that's what we need in order to build the numerator up to what it's going to be. So our PFD equation, in this case it's pretty easy because we have the same factor all the way through. When we multiply everything by x minus 2 cubed, you're going to get a times x minus 2 squared plus b times x minus 2 plus c. Okay? So now we only have one true convenient value, and that's 2. Right? Let's use it because we have it. So that convenient value of x equals 2 is going to give us 4 on the left. When we plug in 2 here, we get 0. Plug in 2 here, we get 0. So we get 4 is equal to c. So we already have our constant. Now for this one, we have 2 choices. We could pick, because we have 3 unknowns, we're going to need to pick 3 values. Or we could pick 1 value and now multiply it all out and go back to the traditional method. So there's a lot of choices. It doesn't really matter which way we go. This time, let's do it that way. So I'm going to plug this back in. So I'm plugging in the c equals 4 right there. Because there is no unknown over here, I'm going to move it to the left. So I'm moving that 4 over to the left. Plus 4 on the left means minus 4 on the plus 4 on the right means minus 4 on the left. And then on the right, I'm going to multiply this out. So x squared minus 4x plus 4. This is going to be bx plus negative 2b. So now we're converting back to the traditional method. So let me just multiply this all out. And then we'll equate our coefficients. So here is our new equation. So we isolate, we had C, we solve for C. Now C doesn't have an A, a B, or no unknowns in it, so I'm just going to move it to the left side where we have all the stuff that is determined already. Right, so there are the unknowns on the right. Let's build our system. So, what's the coefficient of x squared on the left?
1.
What's the coefficient of x squared on the right? What's the coefficient of x on the left?
0.
Coefficient of x on the right, we look over, there's an x, there's an x. So the coefficient of x on the right is negative 4a plus b. Negative 4a plus b. Constant on the left is neg 4, constant on the right. There's a constant, there's a constant. So constant on the right is 4a minus 2b. All right. So now we have two of them already solved. We have C and we have A. To solve for B, we really didn't even need this third equation, right? We could have just solved it right here. Or we could ignore that one and put it here. It doesn't matter which one we use. If we look right here, we know that A is 1, so we plug in 1. That means B has to be positive 4. So B is positive 4. So now we have all three. So our original integral up here, call it W, call it whatever you want. All right, W is going to be A over x minus 2. A, we found to be 1 over x minus 2. And then we have 4 over x minus 2 squared. And then let's see, we have A and B. What was C? C
4.
is positive 4 also. So then 4 over x minus 2 cubed. So that's where we're at. So let's rewrite this. Before we do the integral, let's just rewrite this so that it's a little easier to track. So this is x minus 2 to the negative 2. This is x minus 2 to the negative 3. dx. So that is now ready to integrate. The first one is the easiest one, natural log of x minus 2. Getting good at that one. Second one, we have to use the power rule in conjunction with the reverse chain rule, but not really, because the derivative of those bases is 1. The derivative of this is 1, so reverse chain rule, don't really need it. Derivative of this base is 1, reverse chain rule, don't really need it. So we add 1 to the exponent, getting negative 1. Negative x minus 2 to the negative 1, x minus 2 to the negative 1 is this. The numerator is the constant 4. When we divide by negative 1, that plus becomes minus. This one, add 1 to the exponent, we get negative 2. All right, there's the exponent to the negative 2. So we add 1, get negative 2, divide by negative 2, and it makes the coefficient out in front negative 2. So we'll put that like that, plus c. So there's our antiderivative. Our family of antiderivatives, more precisely. Or the general antiderivative, some books will call it. All right, any questions on that?
Can you also just, when you're deciding how to do it after you get what C was
Mm-hmm.
with the convenient value of 2,
Yep.
can you just pick other numbers?
Yes.
Okay. based
Yep.
off a system equation.
There's so many ways you can do it, you can't even describe all the ways.
Because I did
so-
it that way, I just wanted to make sure I didn't just get lucky.
No, you absolutely can do
Okay.
that. So,
is 0 and
you-
1.
Yeah, you could pick 0 and 1. You could pick 3 because 3 minus 2 is 1. That's pretty nice. So you could pick, the bottom line is there's 3 unknowns, so you have to pick 3 values if you go the value method. Yeah, absolutely. Or of course, we could have gone traditional method the whole way and multiplied this all out. So it doesn't matter. Some hybrid is usually the most efficient. All right, finally to the irreducible quadratic. So irreducible quadratic, that's a quadratic that can't be factored without using imaginary numbers. The classic ones that are obvious are things like x squared plus 1, x squared plus 2, if you have a sum of squares. That's the obvious one that's irreducible. Can anybody tell me, if you're looking at this, how do you know whether it's factorable or not factorable? How do you know whether that is irreducible or not irreducible? Is there a way that you can discriminate whether it's factorable or not factorable? Is there a way you can discriminate? There is a quantity from algebra that has a word similar to discriminate.
Related to that b squared minus 4ac.
So the discriminant in the quadratic formula, negative b equals or minus square root of b squared minus 4ac. The b squared minus 4ac is called the discriminant because it discriminizes zeros, types of zeros. In order for a quadratic to have non-imaginary zeros, that discriminant has to be positive or 0. If the discriminant is negative, then you have the square root of a negative number, which will then generate imaginary solutions. So if you're looking at this, I mean, you could say, oh, well, if I can't find the factors, then it's not factorable. But we all know, we've all stared right at things and not seen them. Just because you've tried a bunch of things and it doesn't seem factorable, that doesn't prove that it's not factorable. So if you want to prove without a shadow of a doubt that something is not factorable, you would look at the discriminant. So you would look at b squared minus 4ac. So in this case, b squared minus 4ac, b squared minus 4ac is going to be, so b squared is 4. Minus 4, a times c is 2, so it's going to be negative 4. So that is how you know for sure that that thing is not factorable and that it has imaginary zeros. So our PFD then, we are going to take this, the original, that original fraction, so this whole thing. We now know that that's not factorable. So here is going to be our PFD for a non-factorable quadratic. So the only thing that's a big difference is that you still have to have your factor in the denominator, but notice what the numerator is going to look like. Instead of the numerator being a constant, the numerator is going to be a general linear expression. So for us, in this case, we'll call it bx plus c since we already used a. So the numerator for an irreducible quadratic is linear. The numerator for a linear is a constant. The numerator is always 1 less in degree. So linear on the bottom, constant on the top. Quadratic, linear on the top. So we're building a proper fraction that's, right on the edge. Right? The numerator, for this to be a proper fraction, the numerator has to be linear or lower. And so we picked the biggest thing that makes it still a proper fraction. And then we do the same thing that we did on the last one. We clear the fraction. So we multiply both sides by that denominator. When you multiply the left by that denominator, you get the numerator. When you multiply the right side by that denominator, you multiply by x, the x cancels, so we're going to get a times x squared plus 2x plus 2. And when you multiply this second factor, that big factor disappears, and you have bx plus c multiplied by x. So that's our PFD equation. PFD equation. Now there is one convenient value that we could use here, or we could just multiply it all out. Doesn't really matter. Let's just multiply it all out because this is a pretty simple one. So if we multiply this all out, we have that. And we should be able to find our coefficients here. You don't have to group these together. You know, you could do one more algebra step and truly group those together. You know, and write it as a plus b times x squared. But we can kind of see that the coefficient of x squared is a plus b on the right. So, coefficient of x squared. On the left, 1. Coefficient of x squared on the right, a plus b. So there's our first equation. We know we need 3 equations because there's 3 unknowns. The coefficient of x on the left, 3. Coefficient of x on the right, there's an x, there's an x. So the coefficient of x, 2a plus c. 2a plus c. So 2a plus c. And then we go to the constant. So the constant on the left is 2. Constant on the right, just this, right? That's the only one that doesn't have an x, so that's the constant. So 2a on the right-hand side, and 2 on the left. So there is our system of 3 equations with 3 unknowns. Right away we see that a is 1. And if a is 1, what's b?
0.
0. And that tells us that c has to be also 1. We plug in a equals 1 right there, 3 minus 2 is 1. So now we have all 3 of our unknowns. So our integral, if we call the thing w can now be rewritten as the integral of 1 over x plus, let's see, b is 0, that's cool. And then we have 1 over this. So we've got that. Okay. So any questions up to the point there where we have to integrate now? Yeah.
Could you go over the first part? Yeah, how did we get the bx plus c in that?
This right here?
fraction? Yeah.
So that's what the new rule, if we have an irreducible quadratic, so if we have a quadratic that's not factorable, then the numerator has to be a general linear expression. So ax plus b, bx plus c, cx plus d. We already used the a, so we're not going to use ax plus b, because we already used a for the linear one. So we just need this to be linear. So anytime we have an irreducible quadratic, we're going to have a linear numerator. Anytime we have a linear denominator, we're going to have a constant numerator. So it's always going to be 1 less in degree. So linear to constant, quadratic to linear.
Yeah, another question, the 1 equals a plus b. How
Yep.
do we determine that b is 0 from that?
I determined it from this.
Oh, okay.
So A is 1, and if A is 1, we're going to plug that one into that.
Oh,
Right, yeah. Yeah, on its own, we couldn't do that. Yes. We have to have that extra equation. Anyone see the antiderivative of the second integral? What's the process, Danny?
I completed the square,
Yep.
and then that's the inverse tangent of x plus 1.
Exactly. So this right here is a quadratic that's not factorable. So we use our completing the square technique, divide this by 2 and square it, and we get a 1. So that tells us that we want to separate that constant of 1 like that. Now we have a perfect square trinomial, and that perfect square trinomial will give us this. That's a plus. So that's a plus integral. So this is going to be x plus 1 squared plus 1. That's in the specific arctangent form already, so we can just integrate it immediately. So we're going to have, as our final answer, natural log of the absolute value of x plus arctangent of x plus 1 plus c. We don't have to deal with any reverse chain rule because it's an x plus 1. It's not 3x plus 1 or something. If it was 3x plus 1, we would then divide by 3. Whatever that derivative would be of this quantity inside the parentheses. So we don't have to deal with reverse chain rule in this case. All right, this one's about as bad as it gets. This one is as bad as it gets. There are 2 irreducible quadratics. Okay, so this first one, that's irreducible, sum of squares. Well, that's also a sum of squares. Right? That's y squared plus the square root of 2 squared. So you can also think of that as a sum of squares. Sum of squares are never factorable without imaginaries. So, here, we are going to have this as our PFD. So y squared plus 1, irreducible. Y squared plus 2, irreducible. So we're going to have each one of these denominators like that. Yeah, we're just going to put a linear expression in each numerator. So we can use AY plus B, and then the next letter available is C, so we can do CY plus D. So that would be our factorization form, our PFD form. And then we're going to multiply both sides of the equation by the denominator on the left. So when we do that multiplication, on the left we end up with just 1. On the right, this double product here has to go to each of these fractions. When it multiplies to the first fraction, the y squared plus 1 cancels, and we're going to be left with ay plus b multiplied by y squared plus 2. And similarly, when we multiply by the second fraction on the right-hand side, the y squared plus 2 cancels, and we'll have y squared plus 1. So that'll be our PFD equation, with absolutely 0 convenient values.
Where'd the C go for CY plus D?
Oh, yeah, that's a parenthesis or a parenthesis right
It's a
there.
parenthesis.
The parenthesis. Yeah, it's hiding. Hiding in plain sight. Thank you. Good eye. All right, no convenient values here, so our only choice is to multiply it all out and go traditional. So FOIL this out, we're going to have ay cubed plus 2ay plus by squared plus 2b. So no other choice here, we just have to multiply it out. Now how many equations are we going to have?
4.
We have 4 unknowns, A, B, C, D. If we have 4 unknowns, we have to have 4 equations in order to solve. So we're going to start with the power of 3. So what is the power of 3 coefficient on the left? 0. Good. And then on the right, we are going to look at all those that have a power of 3, so that coefficient is going to be a plus c for the right-hand side. So there's our first equation. I'm going to try to group the letters. I'm going to stack them, so it's going to be easier to solve the equations in the end. So that was the power of 3. Now we're going to go to power of 2. So there's power of 2, there's power of 2. The left side, the power of 2 is 0. Power of 2 on the right side looks like b plus d. So b plus d. Then we're going to go linear. Linear on the left is 0. Linear on the right. There's a y, there's a y. So the linears, 0 on the left. We have 2a plus c. We're almost there. Constant on the left is 1. The constant on the right looks like 2b plus d. So 2b plus d. So there is our system. 4 equations, 4 unknowns. We need to do some sort of elimination or substitution. Here is what I see. I see that these two can be paired up. Yeah? And if we do equation number 3 minus equation number 1, so 3 minus 1, we're going to get 0. 2a minus a is 1a. C minus c is 0. So we have a is 0. And if a is 0, what is c equal to?
0.
0 also. And then, let's see, let's do equation number 4 minus equation number 2. So if we do 4 minus 2, 1 minus 0 on the left, 2b minus b is 1b, d minus d is 0, so b is 1, and if b is 1, d is negative 1. So now we have all of our 4 constants. So let's just write down, we'll do the integration on Tuesday. So our new integral will be, let's see, what are the zeros? So we have ay plus b. So a is 0, so we end up with b. So 1 over y squared plus 1. Oh, maybe it's going to be easy. And then d is negative 1, c is 0, so negative 1 over y squared plus 2 dy. So we'll just leave it there. We see that they're both going to be arctangents. The second one needs a little manipulation by factoring out the 2, but then it will be an arctangent. So we'll finish up these. We'll do those on Tuesday next week. Wow. What week are we in? Did we just finish
Next
Week
week's
5
October.
or week 6? Wow.
Next week is October. Our next test is the week after that.
Okay, yeah, so we must be finishing week 6. That's amazing. That feels amazing to me. It's always a surprise at how fast semesters can go. All right, well, have a great weekend. Have fun doing math.